There's a big marketing discrepancy between the way household appliances are sold and backup power inverters are sold. Appliance specifications, if you're lucky, will be given in amps. Power inverters are specified in watts. So how do you know whether a particular backup power inverter will be able to run the major appliances you own? You don't. Here's a Lowe's ad for a Whirlpool gas dryer, very similar to the Whirlpool gas dryer that we have. And here are the specifications for that new gas dryer. Nowhere on this page, or anywhere else in the ad, does it tell you how many amps this new dryer consumes. So, when you click on the question and answer tab, the second question asks, what's the amperage of this model? Concentrate on the Whirlpool team answer. As 11 of 13 viewers indicate, it's not helpful. So in this episode of the Backup Power Project, we're going to visit the Pina family laundry room and learn how to estimate the backup power requirements of the major appliances in your home. I don't know about you, but in a grid down, not coming back anytime soon situation, I want clean socks and underwear every day. Clean towels for my shower, and I don't want to have to wash clothes by hand. That's what the Backup Power Project is all about. Continuity of modern convenience. And ensuring continuity of modern convenience can be surprisingly inexpensive once you learn how to do it. So welcome to Laundry Room, Episode 10 of the Backup Power Project. Wondering what it would take to keep your laundry room running in a prolonged power failure? Me too. Let's find out. Now, the tools you're going to need for this job are an AC line splitter. This one's a Southwire brand. It cost me $22 or $23 on Amazon. There are cheaper ones. The people who buy the cheaper ones write that they fall apart, overheat, break the first time they use them. I've used this several times. It's well made. I like it very much. I'd buy another one tomorrow if I needed one. And the second tool you're going to need is an AC DC clamp meter that also has peak inrush measurement capability. Now this one is a B-side model ZT-Q B as in beta 9. There are other models that look just like this that don't have the peak inrush feature. So this cost in, I don't know, $35 or so. Bought it direct from China. So your total cost for these instruments is about $53. This is what you're going to need to estimate your backup power system. Okay, now let's see how it works. Now up here on the wall, we have a regular 110-120 US style outlet. I'm going to unplug one of these. So that's my dryer. And this outlet has these little blocks in them. This is a child-proof outlet. What's not obvious to, or may not be obvious to you, is that normally on a US-style outlet like this, both of these sockets go back to the same circuit breaker. But in a laundry room, this top outlet is on one 15-amp circuit, and this bottom outlet is on a second 15-amp circuit. There's two circuits here, not just one. So right away, laundry room, gas dryer. This is a 2001 Whirlpool washing machine. This is an 89 Whirlpool. So we have 15 amp circuit here, 15 amp circuit here, a total of 30 amp service in this laundry room. Now why is that? Why would this be 30 amp service? Well, we're about to find out. So altogether, we want to take 5 measurements, and I've marked them here. We want to measure the AC line voltage today. It varies from day to day. We want to measure the gas dryer inrush current, so that's what it takes to start the dryer. We want to measure gas dryer run, what it takes to keep it running, and we'll do the same for the washing machine. So we will need to record these 5 parameters to estimate the type of backup power system we need to keep this laundry room running in a prolonged power failure. So the first thing we want to do is take our AC line splitter. We'll plug it into this top outlet. Now, the B-side meter is unique in that it's fully automatic. So all we have to do is turn it on. 2 seconds on that button. It goes into auto mode. You see the word auto? So you don't really have a function and range switch, and we've only got 2 sockets. So red to the red socket, black to the black socket. It makes it very easy. Now what we want to do is take our black lead. It doesn't really matter, but we'll take the black lead, we'll put it into the neutral. We'll take our red lead, put it into the load, and what I'm reading right now, hopefully that's in the camera and you can see it, 124.7. And today is March the 29th, 2023. That's high. Usually this house runs around 121. But that's our voltage today, 124.7. So, okay, we record that. All right, made our first test. Now, what's it going to take to start this gas dryer? Well, we don't need the leads for that. We can disconnect these leads. Now, on this meter, it's going to be different depending upon the meter that you buy. Right here it says DC. That's the default, DC. So we've got to press the select button to change it to AC. Now it says AC, true RMS. Now we've got to press this button here, this blue button on the side, to get it into the peak inrush current mode. There it is. True RMS inrush. And we also turn the light on. That's pretty nice. And we do that on this meter with the blue button. Okay, so now it's ready to measure what it's going to take to start this dryer. So all we have to do is hang it on our AC line splitter. Plug the dryer into the line splitter. Okay, we're ready to measure. Let's turn it on. We got a beep, we got an instant measurement, and it says 405.5. Okay, now the dryer is not drawing 405 amps. Most AC line splitters, which is this piece, force you to divide by 10. So 405.5, we divide that by 10. We've got 2 of our 5 measurements. Line voltage is 124.7 volts. Takes 40.5 amps to start the dryer. Now let's see what it takes to run the dryer. So I just turned off the peak hold. Now we're running the dryer, and so let's round that off to 50 amps divided by 10. That would give us 5 amps. So this only took a couple of seconds. All right, 5 amps to run the dryer. Okay, so we're going to practice now with the washer. So we'll start from scratch. Hold the red button down for 2 seconds. Turns the meter on. Now, the default is DC. We're going to be measuring AC amps, so we want to change that to AC. So one more press. It goes to AC. Then on this meter, we want to use the blue button that's here on the side to select peak inrush. So let's try a couple of presses. First press, it's true RMS. And it should say peak inrush right now. We're ready to go. So all we do now is hang the instrument on the AC line splitter and ready to go. Turn on the washer. Okay, so now we're on the fill mode. And fill mode doesn't draw hardly any electricity. So if you look at the meter, it's really not showing any electricity. See if I can turn on the light. Usually another press will turn on the light. Okay, we got a beep. We got a reading. Let's get it out of there. $274.6 amps divided by 10, that would be 27.5 amps. True RMS inrush, that's our peak inrush current. 27.46, we'll round it off, 27.5 amps. Okay, so what's our running amps now? So I'm going to turn this off. Now we're just on running amps. Clamp it back on the AC splitter. There we go. So there's our running amps. We're running at about 90 amps divided by 10. That would be 9 amps running. So we're 9 amps running. That easy. So now we see why there are two separate 15 amp circuits in the laundry room. The combined peak inrush of the washer and dryer is 68 amps. If both appliances tried to start at the same time, 68 amps would trip the breaker. Even the combined run current of 14 amps is uncomfortably high. In my experience with resistance heaters in our greenhouse, 14 amp sustained current is too much for a 15 amp circuit. Eventually, wires overheat and the outlet melts. It's dangerous. Obviously, any inverter we buy is not going to run both appliances in the laundry room at the same time. And since watts equals amps multiplied by volts, we're going to need at least a 5,000 watt peak inrush inverter just to start the dryer. Since I had previously measured 5 amps operating current with a kilowatt meter, that came as a surprise to me. The peak dryer inrush of 40 amps is 8 times the running amps. 5 goes into 40 8 times. If anything, I thought there might be a problem running the 9 amp washer, but it's just the opposite. Here, we only calculate a little over 3,400 peak inrush watts, only 4 times the running amps. My $130 Jupiter 2000-4000 inverter runs that washer just fine. So, I either need a clothesline or a bigger inverter to start the dryer. Here's what to look for. 3,000 6,000 watts, whatever it takes to operate a 5,000 watt peak inrush clothes dryer. Pure sine wave, low total harmonic distortion, not modified sine wave, which has much higher total harmonic distortion. Wi-Fi and or a Bluetooth remote control, preferably both because Wi-Fi goes further than Bluetooth. We want very low self-consume. Can't have the inverter depleting the battery when it's just sitting there in idle mode. Vertical, not horizontal AC outlets with no mounting lip in front of them, preventing the use of right-angle power cords. See, this lip is no good. Can't use a right-angle power cord with this inverter. And we want vertical battery cable connections, not horizontal battery cable connections, unless you also had a battery with horizontal battery posts. Most batteries have vertical battery posts, so that's why we want matching vertical battery cable connections on the inverter. Okay, with this list in hand, let's go shopping. What about this 3,000, 6,000 watt Jupiter? Would that do it? I don't think so. I don't see how that unit could possibly deliver 3,000 sustained watts. Look at those outlets. They're not even 20 amp outlets. 20 amp outlets have a T-shaped neutral socket. The outlets on this inverter don't have a horizontal slot on the neutral. They look like ordinary 15 amp outlets. Now, let's do the math. Amps equals watts divided by volts. We have 3,000 watt specified inverter power divided by 115 volts specified inverter output equals 26 running amps. 26 continuous running amps from a ordinary 15 amp outlet? It's far more likely that this is just a twin 1500 3000 watt inverter with 25% less peak inrush power than the much less expensive 2000 4000 watt Jupiter inverter I already own. I'm not going to risk it, especially after I read this guy's review.
All I can do is 2 stars because I believe this is 1200 to 1500 watts per 115 or 120 volts plug side split left and right sides, giving it a total of 3k watts continuous. I think if it was 3k watts from any plug at one time it would melt a single plug, or extension cord.
Now, what about this $600 pure sine wave 3000, 6000 watt Jupiter inverter? It doesn't meet requirements 3, 5, and 6 on our list. It doesn't have a Wi-Fi or a Bluetooth remote. We're looking for both. It doesn't have vertical outlets. At least there are 20 amp ground fault current interrupter outlets, so there's a chance it would work. And it doesn't have vertical battery cable connections. I think I'll pass. Right now, a clothesline is looking pretty good. What about peak inrush clamp meters? Can we shop for that? Well, if I needed one today, if I couldn't wait to have an inexpensive B-side sent directly from China, here's what I'd look for. We want both AC and DC voltage measurement, not just AC. We want AC and DC amp measurement. Again, we need both. Data hold. Data hold really helps when measuring hard-to-reach spots. And then the subject of today's episode, AC peak inrush current measurement. We want 5-foot-long flexible test leads. Flexible test leads with half-inch-long bare metal test points. And we want an easily replaced, readily available battery, not some weird battery. What about this $100 Ames clamp meter? Let's check the reviews.
Unable to get inrush current from air conditioner circuit. Ability to test AC and DC. I have had tester for 2 weeks and have used it half a dozen times, but as stated above could not get inrush mode to work.
Peak inrush measurement capability is what we must have. If it's hard to use, if it doesn't work at all, what's the point? On the other hand, if money's no object, if $360 to you is like $36 to me, then there's this amp probe meter. Why is it so expensive? Because it's available today and it also measures total harmonic distortion. Worried about clean backup power for your sensitive electronic components? Me too. We'll find some next time, using this very same, very expensive amp probe in episode 11 of the Backup Power Project. In the meantime, hope this helps someone. Thanks for watching.